So far, we've looked at our confidence in models that simulate mean climate changes over a very slow amount of time, right? Or a long period of time, right? Now, obviously, those are important, right? We need to know mean global temperature, mean global precipitation, and things like that. But that leaves out small scale events, events that happen over a very small space, a small time period. So we need to look at these low frequency extreme events like storms, droughts, and be able to model those as well. So let's think to ourselves, which type of model would be best to simulate extreme events? The general circulation model that has really high spatial and temporal resolution, but leaves out biogeochemical cycles, an Earth system model that includes biogeochemical cycles, but doesn't have a very good spatial or temporal scale, or regional climate models that have both a high resolution and also includes biogeochemical cycles, but only looks at a small space. Right? The answer here, which you hopefully got, was C, regional climate models, because most of these extreme events happen in a small space, right? Hurricanes, they're limited in space. Droughts, they're limited in space. They're not global. So if we can model them at high resolution at a regional scale, that's great. Now, we've talked a lot about uncertainty, how to quantify it, but let's think about, well, where does that uncertainty come from? Why are there errors in our models? And they come from a lot of different places. The first is observational uncertainties. We've already talked about how, we don't have observations from everywhere on Earth, places that are not well populated or not well funded. We just don't have a lot of observations from, and that limits our ability to create our models. There's also resolution uncertainties. We talked about those trade-offs. We can't have the highest resolution that we would want because we don't have that computational power. There's also mathematical uncertainties in describing natural processes. As you know, as environmental scientists, describing the natural system with a single mathematical equation is very difficult to do because, nature is often chaotic. We have to choose a model domain. What space are we looking at? The application of boundary conditions. If we have a regional model, right, there's edges to that region. We have to know, well, what parameters are we putting into those edges? There's feedback uncertainties, choice of included processes. We can't include everything. Threshold uncertainties, things like that all go into making errors and uncertainties in our model. So this is often why we look at the mean of all of the models, hoping that if we run multiple iterations, those outliers will kind of might show us the best and worst case scenarios, but it's way more likely that what's actually going to happen is going to be closer to the mean of all of those model simulations.